Today we are reviewing electric charge, Coulombs law, and let me just get the paint tool up. And today is Thursday, March 9th, 7 p.m. All right. And all right. So all right, ready to begin?
Yeah.
All right. So there's two kinds of charge. What are the two kinds of electric charge?
Conductivity and resistivity.
That's a good guess. That's a good guess. So what you said was conductivity and resistivity. Conductivity is the property of a certain material that allows electrons to very freely move through the material.
Yeah.
So like copper is in most of the wiring that we have, and if not all of the wires that we have everywhere in our houses, in our computers and everything. Wherever you have wires, you know, the outside is rubber, but if you slice that wire open, you'll see copper threads inside.
Yeah.
And so copper is highly conductive, so it has a high conductivity. Resistivity, on the other hand, is the tendency for a certain material to resist the flow of electrons through it. And those kinds of things are called insulators. That's actually in another topic, I think, because what happens typically is you begin with the foundations of electricity, which is learning Coulombs law, the fact that there's positive and negative charges. How do we quantify exactly how much charge we have in a certain point in space? How do we quantify how much force they repel or attract each other with at a given distance? Those are all things we can talk about tonight. Those are the foundations of electricity. Then normally they will build upon this, and this will eventually gear into one of the following chapters, which will be circuits. And you'll start learning more about materials, as we just said, about resistivity and conductivity, conductors versus insulators, how you build circuits, how do you flowing in a certain circuit and such. That all comes normally after this introductory unit, which is kind of more foundational. So we start with the idea that there's two kinds of charge, positive and negative charge, right?
Yes.
What inside of an atom is considered to have positive charge?
The protons.
Yep. And then these would be
the electrons.
Electrons. So let's say this right here. In fact, let me make it a little bigger. Let's say this is the nucleus of an atom. What kinds of the charges that we already listed live inside the nucleus?
The protons and neutrons.
Very good. Yeah. So if you have one proton inside the nucleus, do you know what kind of atom that would be?
Sure.
If you have an atom that has only one proton inside the nucleus, do you know what kind of atom that would be?
No.
That would be a hydrogen atom.
Oh, I didn't know that.
It's okay. Have you ever taken chemistry?
Yes. A while back, like in ninth grade.
Oh, wow. Okay. If you had... Why is my pen is not working? Here it is. So if you have one, I'll just jot a few of these ideas down. If you have one proton, that's a hydrogen atom. if you have 2 protons in the nucleus, then you'd end up having actually 2 neutrons as well. And that would be a helium atom. And so, it's important to recognize that the reason this topic is important is electric charge is a very important topic because all of the atoms in the universe are composed of electric charge. Your whole entire body is completely made of atoms, and one given individual atom has a certain amount of properties. And generally those properties are distinguished from properties of other kinds of atoms by the things we're talking about now. How many protons are in the nucleus, how many neutrons are in the nucleus, and how many electrons does it have surrounding it. And the way that atom can interact with other kinds of atom, like a carbon atom can interact with an oxygen atom, is based upon how many electrons surround that nucleus. That allows atoms to form molecules, and molecules to form compounds and physical body that help us, protein, about protein, chicken and meat. So I'm just pointing out, this isn't like a topic that's just completely abstract and doesn't relate to our lives. Not only is your whole body made up of atoms, but every single thing you touch is made up of atoms, and everything that you see is made up of atoms, and they all kind of share these same similar traits in terms of charges.
Yeah.
Okay, so that said, would you happen to know what the electric charge is called, the fundamental electric charge or fundamental charge? It's okay if you don't know it.
An elementary charge?
Good. Good job. You knew that. Yep. Fundamental charge is called the elementary charge as well. What does elementary mean? Why do they call it an elementary charge? What does that mean?
It's the lowest form.
Exactly. It's the smallest kind of charge. So anything that's elementary means that all other things will build upon it, like elementary school. All other learning in life is built upon what you learn in elementary school. So an elementary charge is the smallest unit of charge that we think that at least when they decided to call it the elementary charge, they thought it was the smallest unit of charge. We now know that it was wrong. They decided not to change the name elementary charge, but we now know that there's things called quarks, Q-U-A-R-K-S, that are charges that are smaller than what we've already called the elementary charge.
It's also smaller than 1.6 times 10 to the 19.
Yep, you got it. Good job. Yep, good, very good. So I'll comment on that in a minute. What's referred to as E positive is positive 1.6 times 10 to the minus 19. C is now the SI metric system unit. Yep, C stands for Coulomb because of the man, Coulomb, who had discovered Coulombs law. This law was named after him, of course. The unit for electric charge was named after him also.
Okay.
So this is a unit for charge. And notice that this is a really tiny amount, right? Because a minus 19 is extremely tiny, right? So that means if someone said, can you write that charge, as a number, it would be 0.00, and I'd have to keep going 19 times, right?
Yeah.
I mean, so I'm not counting, but just trying to prove a point, something, like that, right? It's an extremely small charge. So does it take a lot of elementary charges to form one full Coulomb?
Yes.
Yeah, it does.
I actually wrote that number down.
Oh, okay, great. So we'll come back to that in a second. So the important part to recognize is that that's the charge of a proton. E positive is the charge of a proton, 1.6 times 10 to the minus 19 coulombs.
Mm-hmm.
The charge of an electron is normally written as E minus. So E, again, stands for elementary charge, and then the plus and the minus that's in the superscript is representative of whether it's referencing a positive elementary charge or a negative elementary charge.
Okay.
And so an electron has the exact same charge as a proton, but just negative. So the charge of a proton is positive 1.6 times 10 to the minus 19 coulombs. The charge of an electron is negative 1.6 times 10 to the minus 19 coulombs.
Okay.
So in magnitude, quantity, they have the exact same charge, but opposite in sign and direction. Does that make sense?
Yeah, I got you.
Okay. All right, so this was again called the fundamental charge, often referred to as an elementary charge. All right, I'm going to continue on. You have any questions? Okay, so I'm going to erase this. So first off, let's talk about quantity a little bit more. Here's a question. How many electrons are needed to form 1 coulomb of charge?
Elementary charges?
Yep. So how many, because remember, the electron's charge is called the elementary charge.
Mm-hmm.
Oh, and I said I'd comment about quarks. Let me cycle back just for a second to say that. There are things that have been discovered now known as quarks, spelled Q-U-A-R-K-S. And quarks are, because way back when they discovered protons, they thought that the proton was indivisible. That means that you couldn't pull it into smaller pieces, that no matter how hard you tried, you'd find that the proton is the smallest unit, and you can't smash it against something and make smaller pieces come out. That's what they thought. So that's why they call it an elementary charge, right? But that was way back long, long, long ago. Now we have you heard of, CERN, C-E-R-N? CERN?
No.
Have you heard about the Large Hadron Collider, LHC?
No.
Oh, really? Wow, you're missing out. So you really should know about this. It'll only take about 2 seconds, or not 2 seconds, 2 minutes. It's the biggest science experiment ever gone on in the mankind's history, and it's by far the most expensive scientific experiment that's ever gone into this. And it's too much money for any one nation to afford, so it's an international project that many countries are pooling their funds towards to operate. I'm going to show you a picture. And I'll describe it to you. It's called the Large Hadron Collider, CERN. It's in Switzerland. And what they do is, you see this?
Yeah.
See that picture? So that's, and you see this picture right here?
Yeah.
It's a giant tunnel that's way underground through the shape of a donut.
Okay.
And these are all particle physicists that work there, engineers and particle physicists. And their ultimate goal is to find out what the most fundamental units of matter actually is. You know, they want to know, is there something smaller than a proton? Is there something smaller than an electron? Are there other particles in nature that we might find if we look, even though no one's predicted that they exist? What's their method? They take 2 tunnels. This loop you're looking at is 26 miles in circumference.
Wow.
Very, very significant, right? So 26 miles all the way around, and very deep underground. You have to take elevators to get down there. And they accelerate a positive charge, a proton, up to just under the speed of light, 99.99% the speed of light. And then in the opposite direction, if the proton's going around clockwise, the opposite direction will be counterclockwise. They'll accelerate an antiproton, which is a part of antimatter that makes the antiproton similar to the proton, but it has the exact opposite charge. So it has the same charge as an electron, but it actually has the same mass as the proton. But anyways, the point is that they accelerate these two charges that have opposite charge because opposite charges attract or repel. They attract. And so they accelerate them in opposite directions, both up towards the speed of light, just a fraction under the speed of light. And then they merge those paths and smash them together. And then what you saw in this, yeah, and then what this is, bless me, I have got a cold. What you're seeing in this picture is a camera. That's just like a cross section of this tunnel, and there's $1 billion camera in there. So as soon as they smash this proton and antiproton together, they take billions of pictures just in a fraction of a second to try to capture images of whether there are actually things that will come out of this smashing. Because if the proton and the electron are truly fundamental, then that truly would mean that no matter how hard you smash them together, no smaller parts are going to come out, right? So my point is,
it's a supersonic particle accelerator.
Yeah, it's a particle accelerator. You got it. It's called CERN. Facility to is CERN, ERN, and that actual experiment is called LHC, Large Hadron Collider. The types of particles that they're smashing together are called hadrons. A proton is a type of hadron, just a weird name that they gave for that kind of particle. And so they called it the Large Hadron Collider, large because it's 26 miles around, hadrons because they're smashing this type of particle called a hadron into other hadrons, and collider because they're colliding them.
How do they get the current?
Yeah, they have to take protons and pull them off of atoms and keep them isolated. And then they accelerate them in these giant streams. And it's not just one proton that goes around. It's billions of protons going round and round. And actually, they don't just do one collision and take pictures. They do billions of collisions per second, which is incredible to get your mind around.
I was trying to figure out, like, how do they take like a proton out of an atom? And so, on a molecular scale, how do they see that they have a proton?
So, let me go back to my picture. So when you're looking at a hydrogen atom, it just has one proton and one electron. So if you want to get a proton all by itself, all you have to do is put a flame, meaning heat the hydrogen, provide a heat source to the hydrogen. As you heat the hydrogen, this negative electron will start vibrating up and down in simple harmonic motion, actually up and down. Remember we talked about simple harmonic motion?
Yeah. So
the electron, as it absorbs that heat, will start bouncing. Each time it bounces, it gets a little higher, up to higher energy levels, and then it comes back down, and it goes up a little higher, and then it comes back down. And the hotter and hotter it gets, the higher and higher it will go. And once it gets hot enough, the electron will just pop out and become a free electron roaming around. And that's called ionization when you create an ion. That's called the ionization temperature. When you get a material hot enough, it will cause the electrons to get so hot, because temperature, when we think of what temperature is, it's actually how fast the particles are moving. So like the air in our room, when it's a warm day, those particles are moving very fast. When it's a cold day, those particles are moving slowly. And so when you heat the atom, the electron starts to get more and more kinetic energy as it vibrates up and down. And eventually it has enough kinetic energy to rip itself free. Because remember, isn't the electron attracted to the proton?
Yeah.
Yeah. So it has to have a significant amount of kinetic energy, which it gets from this heating process, and enough to rip it free. And then when it's ripped free, what do you have left behind? Just a proton. Yep. And you can literally capture them. You can move them around. Technically, you can place them wherever you want them, and you can accelerate them and up to huge speeds all by themselves. Yeah. What's that?
I said I understand how they probably accelerate them too.
Yeah, the way they accelerate them is by...
They use a negative charge.
Exactly.
To propel them forward.
That's exactly right. That's very good. Yep.
An electromagnetic charge.
That's exactly right. Yep. So if you have like a negative charge here that's just sitting and you want it to start moving, Well, if you just introduce another electric charge here, which way is this guy going to go?
Go away.
He's going to go away, exactly. And he'll feel a force called the electric force that we'll get to, probably not today, but I'm guessing in the next lesson it'll be about electric force. Actually, no, this lesson, Coulombs law is about electric force. So they'll push apart, right, with a repelling force, right?
Yeah.
And that charge will start sliding to the left, and it will start accelerating. Well, what if this charge right here, as it slides leftward, you keep moving this guy right here and keeping him close to the other one, you know? He like follows him. What would happen to the one on the left?
You're going to keep a constant acceleration.
Exactly. So if you're clever enough about it, you can keep these things moving and keep them speeding up faster and faster and faster and faster. That's a very simplified idea that I just showed. It's not really like that. But the point is, you use other electrons, other charges that repel the one you're trying to accelerate so that it can get faster and faster and faster. Technically, you could also use an attractive charge, because if you have a negative charge here and you put a positive charge on the right, which way will this negative charge go?
We'll go
towards it. Well, if you leave the proton there, it'll just run into the proton. But what if you keep moving the proton to the right?
You'll keep going towards the proton.
At faster and faster and faster speeds, because when you have a constant force, you'll accelerate at a certain rate, faster and faster and faster and faster, right?
Yeah.
Yes, and that's a very simplified idea, but technically that's kind of how they do it. And the way they steer them, they use magnets to steer them. So if you get this electron moving in a straight line at a huge speed, how the heck are you going to turn it? You can technically do it with other charges, like electrical charges, but it's extremely difficult. It turns out way easier if you use other magnets called superconductors, super duper magnets that put out huge strength of magnetism, and you can use those magnets and the magnetic fields that they create to steer electrons. Electrons actually do get repulsed or attracted to magnets as well, and that's the idea of electromagnetism. That you can use magnets to affect electric charge, and you could also use electric charge to affect magnets. They affect each other with a force. And so they use the magnets to steer them in the circle, to change their direction. So the point is that I still haven't gotten to, which is okay, but I'll say it now, is that this is the experiment. So what you're seeing was in Switzerland, and it's still there, and it's still running. The Higgs boson particle?
What?
It's called the Higgs boson.
No.
Higgs boson is referred to as the God particle.
The God particle?
The God particle is what they decided to name it. So that was something they discovered, maybe 2 years ago at LHC. It was a particle that was predicted 60 years ago by name of a man named Peter Higgs, who was a theoretical physicist, and just from his own mathematics, he had predicted that there would be some particle that had certain properties, and that that particle would be very difficult to find, but he was truly faithful that he believed it existed. Everybody thought he was nuts, and he was actually rejected from his scientific community because they didn't believe him. They just thought he was a wacko. But actually what happened is they couldn't do an experiment to prove whether he was right or wrong because they didn't have the technology back then in the 50s. So forward 60 years, now we have all this technology. Once this whole giant LHC came to be, they said, why don't we try to find this particle that Peter Higgs predicted existed 60 years ago? Sure enough, after they smashed them together and looked hard enough, they finally saw evidence that out of the smashing came this particle that had never been seen before. And they decided to call it the Higgs boson. Higgs after Peter Higgs, who predicted it, and boson because that's another kind of particle. It belongs to the boson family of particles. And it was a huge discovery. It happened 2 years ago. So anyways, let me lastly say that what you're seeing is currently running in Switzerland, but in Chicago, there was a very similar particle accelerator, and it's still there, but it was much smaller. And they're the ones that discovered quarks right here in America. And when they smashed a positive charge hard enough in this collision, they found that there were small pieces that came flying out of a proton, and These were called quarks, and they were fractional charges. So a quark can either have positive 2/3 of the, remember the elementary charge we talked about?
Yeah.
So they found out when they discovered quarks that there were in fact smaller units of charge, smaller than the elementary charge, and their values were 2/3. That's why it's smaller, because it's only 66% of E. And there was another quark that ended up being negative 1/3 of E. And this ended up being called the up quark, and this was called a down quark. That's just names they gave them. And so it turns out that a proton, when you smash it hard enough, is made of smaller things called quarks. And it's actually made of 2 up quarks and 1 down quark. Because what is the charge of an up quark? Positive 2/3, right? So what is 2 times 2? So 2 times 2/3 would be 4/3, right? And that would be positive. But since a proton also is made of 1 down quark, remember that the down quark is negative 1/3? See that? So if you have a positive 4/3 Z, and then add to it a negative 1/3 E, what overall charge do you get? What is 4/3 minus 1/3? 3/3, which we just call 1, right?
Yeah.
1E. Does that make sense?
Yeah.
That's what a proton is made of. When you smash it hard enough, 2 up quarks come popping out and 1 down quark comes popping out. And both of those have charges that are less than E. So I would be remiss to tell you that E is the elementary charge and that there's nothing less than that. I'd be lying to you. That's not true. And there's a lot of teachers that do that because they just don't want to waste the time. They want to just try to get through the year. But they're lying to the students because we now know more knowledge than that. And that the elementary charge that you gave me, 1.6 times 10 to the minus 19, is not the smallest unit of charge. Quarks have the smallest unit of charge. But that's, relatively new knowledge.
Mm-hmm.
All right, moving on. How would you answer the question, how many electrons are needed to form 1 Coulomb?
It'd be 6.25.
Yes. How would we calculate that? Because you might have just written it down from your book. How would you calculate that if you were asked to calculate it?
Usually I bounce it on the screen on that.
Okay, so I'm going to show you. The charge of an electron, right,
Yeah.
is negative 1.6 times 10 to the minus 19 coulombs, right?
Yep.
We want to know how many does it take of those to create the number 1? Because we already said that number is way less than the number 1, right? So you would do 1 divided by 1.6 times 10 to the minus 19 on a calculator, and you'll get your answer that you had written down.
6.25.
You got it. Times 10 to the, isn't it 25? Or 10 to the,
Yeah.
times 10 to the,
6.25.
times 10 to the what?
10.
Times 10 to the what?
25.
It is 25. Okay, yeah. So you're asking really yourself, how many times does this charge fit into the number 1? Because that's what division means, right?
Yeah.
So that's a lot of electrons. It's like a trillion, over a trillion, 10 trillion electrons to make 1 Coulomb. So that's an important thing to recognize, that when someone tells you they're holding 1 Coulomb of charge in their hand, that's a whole bunch of charge. That's a lot. Like a lightning bolt might only be delivering 5 coulombs from the cloud to the ground. So, a lot. All right, moving on. I'm going to erase this. So did you try number 2 yet? What's that?
It's not 25. It's 18.
So let me show you.
18.
I'm sorry?
But it's 6.25 times 10 to the 18. I just did it on the calculator.
Oh, I'm sorry. Yeah, I didn't do it on my calculator, so that's what I was asking. I didn't remember what that number was, but yeah, if you did it on the calculator, that's what it is then. 6.25 times 10 to the 18th?
Yeah.
Okay. So notice your first homework problem is how many electrons.
Okay, I accidentally figured it out.
Was that?
I accidentally figured it out on tutoring.
Oh, okay. I'll wait for you. All right. Let me allow you to join. Okay, so your first problem is one we can tackle now. I don't know. Have you done any? You haven't done this yet, have you?
Not yet.
All right. So the method you're going to do this on your own. But there's one thing that I haven't shown you yet.
Okay.
So let's talk about prefixes a little bit.
Okay.
Because those are important to understand. So I have to think for a minute. What will be the ones that are most common in this unit? Micro, nano, milli, and I guess that's it. Okay, so milli is 10 to the what power would be milli. That's the most common guess because milli sounds like million, right?
Mm-hmm.
But milli actually, I don't know why they chose that because it doesn't make sense to me. Milli does sound like million, but it's not. It's not. It doesn't have anything to do with million, believe it or not.
Oh, okay.
So milli is actually 1/1000th of something. 1/1000th of something.
1/1000. Okay.
Yep. Well, heck. How about we do this? You said you want to be an engineer.
Yeah.
All right. So I'm gonna try to support that. So it only takes an extra 2 minutes. I might as well tell you all of the common ones.
Okay.
So, because in my opinion, knowing what prefixes mean is really important. So there's G, which stands for giga, and that
I actually heard of that term.
yeah, giga comes up in computers a lot, right? Like a gigabyte.
Gigabyte.
Yep.
Yeah.
So giga is 10 to the 9th, which is 1 billion of something.
Mm-hmm.
So if you've got a gigabyte of information on your USB, that means you've got 1 billion bytes of information. If you had a giga of anything, I don't know, a gigacoulomb, that means you've got 1 billion coulombs of charge. All right. The next one that's common is capital, and these are both capital. The prefixes will use capitals versus small lowercase to distinguish some of the prefixes. So notice that these are capital.
Okay.
So capital M stands for mega, and that's 10 to the 6th, which is 1 million of something. So if you got a megabyte, you got 1 million bytes of information on your USB flash drive, right? If you got a mega coulomb of electric charge in your hand, you've got 1 million coulombs of charge in your hand.
Yeah.
Got a mega pennies, you've got 1 million pennies in a jar. Okay, the next one is kilo. Kilo is 10 to the 3rd, which is 1,000. Right? Like a kilogram. 1 kilogram is how many grams?
Kilo is 1,000 grams.
How many grams?
1,000.
1,000, yeah, okay. That's right. 1 kilogram is 1,000 grams, because kilo means 1,000, right? How about 1 kilometer is how many meters?
1,000 meters.
Meters, because kilo means 1,000, right?
1,000.
Okay. So that's kilo. So these are all values greater than 1. These are all greater than the number 1, right? Like 1,000, 1,000,000, 1,000,000,000, all greater than 1, right?
Yeah.
The next list is going to be prefixes that mean numbers less than 1. Okay? So I'm going to erase all this. And you should know that the prefixes I've just shown you probably won't turn up in this unit.
Okay.
But if you go into engineering, you're going to be doing stuff with computers, and you see the gigas, the megas, and the Ks, kilos, often are very much used in computer industry.
Okay.
So now let's do numbers that are less than 1. Not numbers, but prefixes. So the first common one would be C. Oops. The first common one would be cent. And centi is just the letter C, and that means 1 out of 100 of something, 1/100th of something, like a centimeter, right? A 1 centimeter is 1/100th of a meter, right?
Yep.
Yeah. How many cents do we have in a dollar?
100.
Is that why we call a penny a cent?
Yeah.
Yes. How many years in a century?
100.
That's right. So anytime you see the prefix cent, it's always meaning 1/100th of something, typically. Like a penny is 1/100th of a dollar. 1 out of 100 is called a cent. So the next one is milli. This one is where you will see these. Yep, you will see in electricity unit. These are the ones that you'll see. Milli is little lowercase m, not capital M because that's mega. Remember?
Yeah.
Yep, and that's 1/1000th of something, which is really 10 to the minus third, right?
Yes.
And then 1/100 is 10 to the minus 2. Because 10 to the minus 2 is the same thing as just moving it down to the denominator and changing the sign to a positive, right?
Yeah.
So you see what I'm showing up here? You see how that works out? 10 to the minus 2 is the same thing as 1/10 squared, which is 1/100, right?
I do see that, yeah.
Okay. Then after centi, then milli, then the next one is micro. And that's the one that's in your problem for number 2. This is called micro, which is 1/1,000,000th of something. And that's 10 to the minus 6. So that's one. If you've got 1 part out of 1,000,000 parts, you're holding a micro of that, as a unit. So they often refer to microbiology. You've probably heard that before.
Yeah.
Because they're using, magnification that is able to study atoms and things that are on the micro scale, which is 1/1,000,000th of a meter. The tiny, tiny scale.
Gotcha. Yeah.
And then there's the nanoscale. We can go down to the nanoscale now with like electron tunneling microscopes, and these very highly sophisticated microscopes can actually zoom in so close on material that you can see things that are on a 1 out of a billion, 1/1,000,000th of a meter. Think of a general regular meter stick.
Mm-hmm.
How many little tiny, you've seen meter sticks before, I'm assuming?
Yes, of course.
And then how many tiny lines are on that meter stick? The tiniest lines that are on that meter stick are those are the millimeters.
Yeah.
So you'd count 1,000 of those tiny lines on a meter stick. You'd see there's 1,000 of them, right? If you looked at one, pair, one little tiny dash and the next tiniest dash on that meter stick, you're talking about the thickness of the human hair. That's 1 millimeter, right?
Yeah.
You'd have to take that human hair and divide it how many times so that you could pull one of those new pieces out and say, I'm holding something that's as thick as 1 nanometer. If you've got something that's only, if you've got something that's only a millimeter thick, and you can go in with a razor and slice it up in equal increments, so that in the end you pull one of those very fine ones out and say, this is a now millimeter thick. How many slices would you have to do to that millimeter?
We would have to cut it up.
Because nano, let me show you, nano is the letter N, is 1 out of a billion, which is 10 to the minus 9. So if you compare the 10 to the minus 3 for milli and 10 to the minus 9 for nano, what's the difference between those exponents? 9 and 3, what's the difference?
Say that again?
What's the difference between the number 9 and 3? What does the subtraction of those two numbers provide?
Oh, 6.
6. So that means you'd have to take a millimeter and divide it 10 to the 6 times. That's the word a million, right? So you'd have to take something as thin as a human hair, which is a millimeter thick, and divide it into 1 million more equal parts. Then when you take one of those parts out, how thick would it be? 1 nanometer. Does that put in perspective how tiny a nanometer is?
Yeah, I do see that, yeah.
Yeah, it's remarkable. Microscopes. Okay, so you have all that? So let's look at, okay, so let's look at your problem. Before I give you a moment to solve it, let's just write down the number. The number in that number 2 that you're going to try says that the charge is 48 microcoulombs. So using this chart here, what number would you put into a calculator for 48 microcoulombs? It can't just be 48 by itself, because 48...
It's going to be 48 times, this is number 2, right?
Yeah. Use the chart, and now notice the prefixes is this one right here.
Sorry, I was on the wrong page.
That's okay.
Reading the wrong number.
That's all right. I'm on number 2.
Okay, yeah. So you're gonna put negative 48 times 1.6 times 10 to the negative 19 coulombs inside of the calculator.
So you'll only reference the 1.6 times 10 to the minus 19 when you're dealing with electrons. And okay, so I think there's some confusion. So you're right. You read the word electrons in number 2. But let me just point out, let's just ignore what number 2 says, and let's just do this problem that I'm doing here on the whiteboard. Let's say we have 48 microcoulombs. That symbol, see the little U with the tail on it?
Yeah.
That's the symbol for micro. So if I asked you, how can we stick that number into the calculator? What number would we add into the calculator? It would be 48 times 10 to the what?
10 micro, so 1 times 10 to 1 over 1 million.
Yeah, but use your 10 to the, see all of these over here?
4 times 10 to the negative 6.
Yes, good, exactly. So when you would go to a calculator to deal with that in a problem, you would type in 48 times 10 to the minus 6, because that value is equal to 48 microcoulombs, 48 millionths of a coulomb.
It would be negative 4.8 times 10 to the minus 6. And then that would be...
No, it would actually just be, I was dealing with the number 48. So it would just be...
Negative 48?
Yep. Yeah, don't worry about the negative for now. I just wanted to get you practice with using the prefixes and turning them into something in scientific notation.
But would it be 4.8?
Well, we can leave it as 48 times 10 to the minus 6, and that could go into your calculator, and that would be fine. But if a teacher said, no, I want it in scientific notation, then you'd have to write 4.8 times 10 to the what?
Times 10 to the negative 7.
Wait. It has to, so to the negative 6 means it has to shift to the left 6 decimal points, right?
Yeah.
So if you decide to make it become the number 4.8, you're already. So how many more do you have to go to the left?
5 more.
5 more. So that's why it would be 4.8 times 10 to the minus 5.
Okay.
That can be a little tricky sometimes. But do you have to put it into your calculator as 4.8 times 10 to the minus 5? Or can you just type in 48 times 10 to the minus 6?
So you can type 48.
Yeah.
10 to the minus 6.
Exactly. You would only do that last thing if a teacher was forcing you to do it.
Okay.
Yeah.
So I got 4.8 times 10 to the minus 5.
Yep. So now let's tackle the problem. I'm going to erase all the board. And you can try it because it's kind of combining everything we've talked about so far, which is how many electrons make up a charge of negative 48.0 mu c. Hello, I'm here.
Yeah.
So how are you doing with it?
I got a little lost.
All right, let me help then. So remember before we said how many electrons would it take to make 1 Coulomb? Remember that one?
Yeah.
And we took the number 1 and found out how many electrons, because each electron has a charge of 1.6 to the minus 19.
Yeah.
So it means how many of this fit into this, right?
Yeah.
So how can we do it if the number is not 1, but the number 48 microcoulombs?
Mm-hmm.
We can write 48 times 10 to the minus 6 coulombs. This is the total charge. And then we're going to divide it by 1.6 times 10 to the minus 19 coulombs, right? Find out how many electrons it takes, how many electrons, because each of these is 1.6 to the minus 19 coulombs times 10 to the minus 19. Each electron has that charge. So when you divide, you're finding out how many electrons does it take to fit into here.
I see.
So on your calculator, you would type
48 times 10 to the negative 6.
Yeah, making sure that's in parentheses on your graph. I'm assuming you have a graphing calculator.
Yes.
Okay. Now divided by parentheses again.
Open parentheses, 1.6.
Yeah.
Times 10 to the negative 19.
Yep.
Close parentheses. That should be so I got 3 times 10 to the 14.
Yep.
So it's going to be a negative. There you go. Because it's still negative 48 in the beginning. So
right. So you're just providing a number like 5, 10, 20.
That doesn't matter if it's negative or positive.
Yeah, the negative is just there to indicate that the electrons are negative, and that if you have if you have 3 times 10 to the 14th electrons, then you have a total of negative 48 microcoulombs, negative because all of those electrons are negative charge. So when they're asking how many, you don't have to reference a negative sign, you just provide them with a quantity.
Yeah.
Because technically, in my ratio that I've shown on the whiteboard, wouldn't the 48 have been a negative here? Notice they gave a negative, right? Negative 48?
It would be, yeah.
And then what would the denominator sign be for the charge on an electron?
Positive. I mean, negative.
Negative.
So it would still come out to be positive.
Yeah, and a negative divided by a negative would come out as positive. Yep. All right. How's that? All right. Do you have any questions on that one?
No. It was clear. I was just a little lost on the conversion part.
That's okay. So let's jump into Coulombs law now.
Okay.
And I'm going to do it relatively quickly, and then I'll let you ask questions. Coulombs law is the idea that you can calculate the attractive or repulsive force between charged particles. This force is known as the Coulomb or more commonly, that's the word commonly, sorry. The electric force. So most people would refer to it as an electric force, right? The idea that if you put a positive charge here and a positive charge here, and let's say we're focused on, we're going to analyze this one. Which way will the one on the left be feeling a force? Will it be pulled toward the right or pushed toward the left?
Pushed toward the left.
Exactly, because you already know that that I didn't mean to say. Yeah, I didn't mean to say that. I'm sorry. You already know that similar charges repel and opposites attract, right?
Yeah.
So it'll get pushed to the left. And remember, we used to do free body diagrams a long time ago.
Yeah.
Same idea, right? You could draw a free body diagram for that and show that it's feeling an electric force to the left. Okay? Excuse me. Thank you. So it turns out the amount of, well, it turns out if you moved this charge, a little closer, like over here, would it feel the same amount of repelling force, less repelling force, or more repelling force if we moved it to that new spot that I drew in there?
More repelling force.
Exactly. It would be a much larger, it would be more. Because it's closer, right?
Yeah.
So let me just make myself some more room. I'm not doing a good job at this drawing, so I'm gonna do it over. So let's say there's a positive charge over here, and you put the other positive charge here, it'd be lots of force. If you put the other charge over here, it would still be pushed away, but with less force. And then if you put that charge all the way over here, it would be even less force. You see how I made them smaller?
Yep.
So this is also the symbol for charge is Q.
Yeah.
So this is, all examples of the same charge at different positions. And this is some other charge. position 1, at position 2. Right, so as r increases, because r is now the distance from this charge to this charge. It's actually a vector, so this would be like r3 because it's, you know, position 3. r2 would be the distance all the way from here to here because it's considered position 2, right? Then r3 would be the distance from here all the way down. Oop, that was hard for me to keep going like that, right? That would be considered r3, right?
Yeah.
So as r increases, what's happening to the force?
As r increases, the force is dissipating.
That's right. Good. Yep. So as r increases, the electric force is decreasing, right?
Oh, you're showing me the formula right now. Okay.
Yep. So that means they're inversely proportional, right?
Yeah. So it'd be in the formula, it'd be divided by r.
Exactly. Yeah. And that's true for you know, so many things in our world. You know, the loudness of my voice in your phone right now depends on the distance between me and the speaker on my speakerphone, right?
Yep.
If I get further away from it, what happens to the loudness?
It dissipates.
It gets less. Exactly. Larger distance corresponds to quieter voice. If I'm flashing a flashlight in your eyes, it's super bright. If I take it further from your eye, what happens to the brightness of the light in your eye?
It
Decrease. It's an inverse, right? Waves. As waves, you know, spread out over the ocean and get further and further away, what happens to their height?
They decrease.
They typically would decrease, right? So I'm just pointing out that's a very common thing. An inverse proportion is a very common feature of physics, laws of physics. And gravity is the same thing, right? As two planets get further apart, do they pull on each other with more or less force? If two planets are further apart than some original distance. Jeremiah?
Yeah.
If two planets are pulled to a much further distance apart, what happens to the force between them, the gravity force between them, if they're further apart? It decreases, right? It's the same idea. Okay, so there's that. And then let me actually tie you back into remember Newton's law of gravitation?
Mm-hmm.
So I'm going to actually do that with you now here. Because you'll see that they're almost the same.
Yeah, that's exactly what one of the videos did.
Yep.
The Newton's law of gravitation, they actually compared it to.
Yep. So if this
I remember I told you when I looked forward, I looked into it.
Yep. So if this is planet 1 and this is planet 2, and there's some distance between them, we call that r. Then, as you just told me, it has to be in the denominator, right? Because they're inversely proportional. More distance between the planets, less force. It ends up being a square because that's actually referred to. This idea that these are like this is called the inverse square law. It's a very well-known and famous law of physics, which means that this means if you double r, if you double r, the gravity force will go down by what factor? Nah, be careful. Remember, you told me it's squared.
Double r.
Yep, if you take the two planets and make them twice as far apart, by what factor does the gravity force decrease?
Factor of 1.
Nah, as a factor, imagine putting the number 2 in here now, and then apply the square is, goes down by a factor of 4. Right?
Okay. Yeah.
Let me show you something else. Let's say we had y equals 1 over x squared. Same idea, just math from a math standpoint. Y's and x's, right? Let's say I have x equals 2. What will I get for y? It'll be 1 over 2 squared, which is 1/4, right? Now, what happens if I double x? I'm going to double x to become the number 4, right? What do I get for y? It'll be 1 over 4 squared, which is 1 over 16. How many times smaller is 1/16 compared to 1/4?
4 times.
4 times smaller. You see that?
Yes.
So that's the idea of the inverse square law. If they get 3 times further apart, by what factor does the gravity force between the planets decrease? 9. Good. If they get 4 times further apart,
16.
then the gravity weakens by 16 times. It would be 16 times weaker of a force. Yep. And we're doing this, I think, is important because you're going to see Coulomb's law is exactly the same idea. And then if the planet got bigger, I always lose my, there it is. If the planet became more massive, a giant planet, what would happen to the force between the 2 planets? Yeah, if one of the planets was a much larger, massive planet, would there be more gravity between those 2 planets or less gravity between them because there's now a larger, more massive planet involved?
More gravity.
More gravity, which places the mass in the numerator or the denominator?
Numerator.
Numerator, yep. So it's the mass of planet 1 times the mass of planet 2.
Planet 2 times a constant.
And which would be the universal gravity constant, right?
And it's similar to electricity.
It's exactly the same. It's exactly the same as electricity. Obviously, you know who Einstein was, and he spent the last part of his life. He was living in Princeton. He was a fellow had fellowship at Princeton University, and he was spending the last 20 years of his life before he died, because he loved this idea that we're talking about. He saw that gravity formula looked like this, and he saw that Coulomb's law looked the same. And he was trying to unify those 2 ideas to create some more universal law that united electricity and gravity into one more masterful law. It's called the unification process, unification theory, trying to unify all the laws of physics into one master equation. And he was unsuccessful. He died, and no one to this day has been able to do it. But my point is, he was so enamored by this idea that they looked the same that he was convinced there must have been some more physics to be discovered. He didn't think it was a coincidence that the formula for gravity and the formula for electricity was the same. He thought it was a hint to him that there's something more to understand as to why those were the same.
Then he tried to unify, he tried to make one master equation for everything.
Yes, yep. It's called, by the way,
So many factors that you have to put into that.
it's actually called TOE, which stands for the theory of everything. And so that's considered the holy grail of all. Yeah, it's the holy grail of all physics, is that you could have one master equation that all of the known laws of physics would come out of that one equation.
And you would be able to solve for everything.
You would be able to solve any possible thing that could possibly happen in the entire universe using one equation. It's called the theory.
Change around,
Right, I know. It sounds crazy. Because as it currently stands, you want to solve an electricity problem? Oh, there's an electricity formula for that. Oh, you want to solve a planet problem? There's a planet formula for that. And these people, like Einstein said, I don't like this. I wish we could become more intelligent, more clever, and wrap all these things into one equation that we could use for everything. It would look simple, but in use it would be very complicated. You probably need computers to analyze it, use it.
Of course.
Yeah. But that was his whole goal. He spent the whole end of his life trying to do that. And to this day, there's still people living out their lives just like Einstein was, and no one's done it yet. It's called the TOE, theory of everything. It's like, if they could figure that out, we believe we'd be much more powerful of a species. Okay, so moving on. Let's do Coulomb's law, because you now see it's the same idea. We'll do it relatively quickly so you can do some practice with it. The electric force between the charges, right? You have a positive charge here, you've got a positive charge here, and they're separated by some distance. And you should know that distance is actually the distance from the center of one of the charges to the center of the other charge. And that's also true for planets. Yeah, it's true for planets too. It's not the distance from the surface of one planet to the surface of the other planet. It's actually the distance from the center of one of the planets. That's a little bit of a small detail, but I might as well tell you that. And similarly, they call this distance r, right? And you know it's going to be an inverse square law, right? And, yeah, and it turns out that if this one is called Q1, some amount of charge, and this one has some amount of charge, let's say, for example, this is 2 coulombs of charge, and this one is 4 coulombs of charge. And the force that they feel is the product of their charges, just like before, remember, it was the product of the masses of the planets?
Yeah, times the constant.
Times a constant, which is called K, yep, which is 9 times 10 to the 9th.
Yeah.
It's an electricity constant, and also seeing that capital G was like a gravity constant, right? The universal gravity constant, capital G. It's a proportionality constant. So, so how would you solve this problem that I've written right here? If I gave you R is, 5 meters, could you try it? Notice there's 2 coulombs on the left, 4 coulombs on the right, and they're separated by 5 meters. And don't bother using K. You could always multiply your answer in the end by K. But just a waste of time right now. But how would you just show me what the number would be in terms of K? 2 times what?
2 times 4.
Yep. So it'd be 8 in the numerator.
Divided by 10.
Yep. Divided by 5 squared. So it'd be 8 divided by 25, whatever that comes out as, times K, right? Because there's this K here. Yeah. And you could always do that in the end on a calculator, times, and then you put in 9 times 10 to the 9th, right?
Yeah.
And also, let me point out, and I think one of your problems, number 10, that you have to do is related to this. The gravity constant is 6.67 times 10 to the minus 11. That's a really tiny number. You to the minus 11 is 0.00000011 times 667, right?
Yep.
Look how big the electricity constant is.
It's a million.
That's 9 billion.
Billion.
Yeah, good guess, but 9 billion. It's a huge value, and that's alluding to the idea that electricity in our universe as a force is way, 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 way stronger than the gravity force.
Yeah, so I'm trying to figure out how to make this one unified equation.
Yeah. If you want to do that,
So many factors.
that would be quite the commitment. That would be tremendous if you could work this out.
Day and night.
That's what Einstein did. I heard from what I read, he wasn't very healthy at the end of his life. He was so obsessed with the problem, he got very little sleep, didn't eat as well as he was supposed to be, didn't move around. He was supposed to be, moving his way, obsessed with his problem, and died with the pad of paper in his lap. When his nurse finally came back to see him, he was dead in his bed with his giant pad of paper with all his equations, just sprawled out on his dead body. What's that? What's that?
I said, I just want to see the notes thing.
Oh, I know. And this is interesting, of course, nothing to do with your, what I'm teaching you, but interesting history. He was the one that published E equals MC squared.
Yeah.
And that equation was used without that equation, they couldn't have created the nuclear bomb. The hydrogen bomb was a result of a powerful and new equation that Einstein had published at that time. He didn't publish it wanting people to use it in a bad way. He was just publishing it as, here's a law of the universe that I've discovered. And then when it got in the wrong hands, they realized they could use that on the atomic scale, that knowledge that the energy stored in the atom was equal to the mass of the atom, the hydrogen atom, times the speed of light squared. And with that very simple equation, they could develop a very complex nuclear bomb, right?
Yeah.
And so often what happens, and like when Einstein died, guess who came right away into his room other than his nurse?
I'm not sure.
The government.
Oh, yes.
You better believe it. Because if there was something in his room, who wanted it? The military. The government and the military wanted that, right? So they rushed his room once the news was out that he was dead. They were there instantly. That's what they did. They took all of his paperwork, confiscated all of it, took it. Yeah. And said, if there's any secret in here, like equals MC squared, it's ours. Yep. Messed up, right? Yeah. All right, so try number, you might as well try number 4 now. I guess you're ready for it.
So, what is the repulsive electric force between two protons? So we'll have something to make the 15 meters apart from each other in an atomic nucleus.
So I'm going to go ahead and erase this.
In an atomic nucleus, so that means that there's a set number of charges.
So I'm going to draw it big for you.
Okay.
So they're saying let's imagine a nucleus, right? And let's imagine that inside the nucleus you've got one proton here and one proton here, and that the distance between them is a really tiny distance, right? 4 times 10 to the minus 15 meters. So you notice it's kind of the same kind of problem that we talked about. What would the charge of the proton be? E positive. No, there are 2 protons, I think it says, right? Yeah. What is the repulsive electric force between 2 protons? So what will the charge for this one be, which we could call Q equals, and then for him, Q equals, what would that value be for their charge?
126.
Yep.
And 19.
Yep.
And 19.
19, what unit now?
Oh,
Yep. And over here, what would be?
it would be the same thing.
Same thing, because it's another proton. You got it. So now really what you got to do is just utilize Coulombs' law. And I'll write it one more time right here. That the magnitude of the electric force that one of them feels will be K times Q1 times Q2. That's the product of their charges. All divided by the distance between them squared. Can I make a suggestion? Well, let's just see. I'll let you go. Because I know that there are sometimes students make mistakes when they put this into the calculator. I don't know if I showed you that before, but
distance in the calculator?
Yeah, when they try to put this whole thing, because there's a lot going on in this equation here. Where's my? Oh, there we go.
When I put it in the calculator, before I put the top number, and I write down that number, and then I would square the bottom number, and then I take that square number and divide it by the top number.
Okay, can I show you even a better way?
Okay.
Because once you learn this, you'll recognize it's good. It's a good way to do it. So just clear out your calculator.
Yeah.
And I'm gonna just write this one in on the board if you don't mind. Then we'll do it on the calculator.
Sorry.
So the denominator, I'm just writing it out right now, is going to be 4 times 10 to the minus 15 squared, right?
Yep.
And then the numerator is going to have our 9 times 10 to the 9th times 1.6 times 10 to the minus 19 squared. And I'm showing that as squared because it's the same number times the same number, right?
Yep.
So this is the nicer way to do it. So let's start with the denominator. So before we do this, I have students that hand in things all the time that are writing it down the way I did, and I can see they understand it. But then when I look at their answer is wrong, it's because they're making a mistake on their calculator. And then there's other students that might be, getting the right answer, but they're writing all these huge numbers down on paper. They don't have to do that. So I'm going to show you this easier way. Start with the denominator. So type in 4 times 10 to the 15th. I'm sorry, I meant to say 4 times 10 to the minus 15. Yeah? And then square and then enter. What number did you get?
10 to the negative 29.
Good. Now there's a button above the on button on the bottom left. It says STO, which means you can store that previous answer as some letter in the alphabet. So go ahead and press STO one time. It says ANS, which means I'm going to store the last answer, the 1.6 times 10 to the minus 29. I'm going to store it as a letter for you. Press X, which is right under the mode button. And then hit enter.
Press X?
Just X. So it says ANS, arrow X, and then hit enter.
Got it.
So now hit type 10 times and then press X, enter. You see, it's just referencing that number now and multiplying it by 10 for you.
Yeah.
It's storing that number as X, so you don't have to write it down, right?
Okay. Yeah, I got it. Yeah.
So now we have our denominator squared, and we've got it stored as a value X. Now we turn our attention to the numerator. So put in 9 times 10 to the 9th. And make sure you're in parentheses for scientific notation. 9 times 10 to the 9th, close parenthesis. Then open parentheses. 1.6 times 10 to the minus 19, close parentheses, square. And then enter.
Those parentheses, that's good.
The last part of the numerator was 1.6 times 10 to the minus 19, then close the parentheses and then press the square button.
Okay.
You'll raise to the second power and then hit enter.
I got 2.3 times 10 to the negative 28.
Yep, now just divide by what?
Divide by X.
Yep, divide by X, enter. There's your number. There's your answer.
8.04.
Yep, I got 14.4.
14.4.
Yep, 14.4 newtons. So you can still do it whatever way you were doing before, but I wanted to show you that way because I found that way useful and I could always rely on it. Some students try to put all of it into the calculator all at once because they just feel like they only want to hit the enter button one time. And I warn them, I say, you can try it, but you might end up making a mistake. And 9 out of 10 times, they make mistakes. They don't get the right answer.
Okay.
So,
I already used that.
what's that?
I already used that.
Yeah. When someone showed that to me, I recognized it was useful. And I didn't have to write all of them down on the paper anymore either. Now I'm going to ask you a question, a couple concept questions. The first one would be, if we had to draw a free body diagram for Q1 and a free body diagram for Q2, what would those free body diagrams look like?
Charging, positive charging.
So our free body diagram is going to depict the forces that these objects feel.
Okay.
So we don't have to necessarily show that they're positive or negative. We could if you want. I don't mind doing that, but that's not common. Which way the forces are as vectors and labeling what those vectors are, what those forces are.
I was asking whether to their charges, we need to know which, like, positive or negative forces acting on them to draw the forces.
Well, so that's what I want to make sure you understand. Let's look at my picture. Q1 is positive. Which way will he feel an electric force? The guy that's on the left. Because there were two positive charges that were separated in the nucleus, right?
You feel a force to the right.
So similar charges, positive and positive, attract or repel?
Repel.
So which way would that move the Q1?
To the right. So you feel a force to the left.
So which way will Q1 move?
You asked which way would move to Q1?
Yeah, which way would Q1 move? To the right or the left?
It moves to the left.
So which way is he feeling a force then?
To the right.
Yeah, if you feel a force to the right, you're going to move to the right, no?
If you feel the positive force to the right.
He's feeling a force to the left, and that's why he would move which way? That way.
To the left. But like if he's feeling a pushing force to the right, when he moves to the left.
Yeah, so that other guy, Q2, is pushing him to the left. He's pushing him away. So this is the force from Q2. Q2, you see what I mean? Q2 is pushing him away, and so that represents a leftward force that he feels from the other charge, Q2.
Gotcha.
Yeah? And then what would the Q2 diagram look like on the right?
Same, just opposite direction.
Yep, exactly, this way.
Push to the right.
Yep. And this would represent force from Q1. Does that make sense?
Yeah.
What would the magnitude of this vector on the left be? This one over here. What would the length of that vector be based on calculation?
It will be equal to Q1's vector.
How many newtons of force did you calculate?
Oh, you're referencing it to the
Yeah.
to the problem.
Yep. So how long would that vector be?
It would be 14.4 newtons.
14.4 newtons. And you'd reference that as the magnitude of the electric force. If someone said, show it as a vector, you can do that. You'd say Fe in the x direction as a vector. And you'd say negative 14.4 because negative means to the left, right? Does that make sense? But if someone just asks for the magnitude, you just provide the positive value, the absolute value, right?
Gotcha.
Okay, and now if we go over to the guy over here on the right, how long is that vector? What's the magnitude of that vector? You got it. Does one of Newton's laws state that those have to be equal and opposite in direction?
Yes.
Yeah. Do you remember which one? It's okay if you know.
No.
It's the third. The third law states that all forces in the universe felt between two things that are pushing or pulling on each other will always be equal in magnitude but opposite in direction. Right?
Yeah.
Yeah. And is that what we're seeing? Yeah. The guy that's on the left will feel a force of 14.4 newtons to the left. The guy that's on the right will feel a force of 14.4 newtons as well to the right. So the quantity of force is the same for both of them, that they both feel the same amount of force, but in opposite directions. Right?
Yeah.
So is that only because they were the same charge?
Yes.
So let's say this is plus 2 coulombs, and let's say this is plus 4 coulombs. If this guy feels a force that's like this, will this guy over here feel less force, more force, or the same amount of force? The 4 coulomb guy on the right. If the charge on the left is 2 coulombs, and the charge on the right isn't also 2 coulombs, but now it's twice as much, 4 coulombs, will they still both feel the same amount of force, but in opposite directions? Or is that only when they have the exact same charge?
When they have the exact same charge.
Newton's third law. What does Newton's third law say? No matter what. Yep. No matter what. So you see that idea? So if this was 5 newtons of force, this one would also be 5 newtons of force. It doesn't depend on how much charge each of them has. Two objects in the universe will always pull or push on each other with equal forces but in opposite directions, no matter what. So, for example, my weight, mg, my mass is about 80 kilograms, and g is, roughly the number 10, right? So my weight is about 800 newtons. So that means the Earth is pulling me downwards with 800 newtons of force. How hard am I pulling upwards on the Earth? 800 newtons, exactly. Me and the Earth both pull on each other with equal forces, because that's what Newton's third law says. Two objects in the universe will always pull on each other with equal forces, but in opposite directions. I'm being pulled which way? Down. I'm pulling the Earth which way? Up. And it pulls me down with 800 newtons, no weight. I'm pulling the Earth up with 800 newtons. That's an important idea. It's a big idea. All right, so good job. You did number 4. Let's see what number 6 looks like. I think you could try it. Why don't you try number 6? I think I think we've done enough for you to give it an effort on 6.
Who charged
And let me show you something. Remember, you can write this as a proportion, right? And you remember those powerful ideas that if R increases by X, then the electric force will increase or decrease?
Electric force will increase.
Decrease times whatever X is squared.
Yeah.
If R, on the other hand, decreases by some value X, then the electric force will do what?
Increase.
Increase times whatever X was squared. That's a powerful tool, so remember that one.
Got it. Of course. What is this charge here? What will be the force? That's the 1/8 as far apart. Almost 1/8 of 4 points. Yeah.
And can I point something out?
Yeah.
Could you even use the full equation based on the information they gave you, K, Q1, Q2 over R squared? Is that even useful at this point, based on what information they provide in the problem?
No.
No. Do you know what Q1 is?
No.
No. Do you know what Q2 is?
No.
No. What's the only way to solve this problem? Using a proportionality.
Yeah.
Recognizing that if you actually change the distance between them, is the actual charges going to change? If you move them closer or further apart, will Q be a different value?
Yeah. No, Q would be a different value.
Right. As they get closer or further, their charge is still the same. And so that's the power of the proportionality. You eliminate the things that aren't changing. Like, is K going to change when you make them closer or further apart? No, that's a constant of nature. Is the physical charges going to change from all of a sudden from 2 coulombs to 4 coulombs because you made it go further apart? No, right? So those are things that are not changing when you change the distance, and so they can be eliminated. That's why we only have the number 1 in the numerator in this proportion here. And you just hone in on the things that are changing. The distance is going to change, and as a result of the distance changing, the force they feel will change. And you can apply those proportionalities and get an answer to their problem without ever even knowing what Q or Q1 or Q2 were.
But like the thing that throws me off, it says 1/8 the distance. Like,
all right, I will give you a little bit of help, but I'm not going to do this for you. So let's say, for example, you have a distance originally of 8 meters between them. What if you now are 1/8 of that? What distance would you now have? You start off 8 meters apart, and then you're now going to be moved closer, so that the new distance between you is only 1/8 of the old value. What would that new distance be? 1, exactly. So by what factor is the distance decreasing by as you go from 8 meter distance to 1 meter distance? Yep. So now you're working here, right? You see where I'm pointing to? R is going to go down times what factor? 8. So now continue with that proportion. You got it. So if they are 8 times closer, that means the distance between them, R, is going down by a factor of 8, which means the electric force is going to go up by a factor of 8 squared, which I heard you say is 64, right? So it's going to get 65 times strong. I didn't mean 65. 64 times stronger of a force. Do you know what the old force was?
No.
You sure? Read it.
Oh, the old force would be 8.
Did they give you the original electric force that they felt when they... Yeah. So if now you know that it's going to be a 64 times stronger force, how could you work what that new force is? You got it. By 64. Yep. Yep, 2.68 or 2.69 or technically, I suppose this would be 2.69 newtons. Yep, 2.7 newtons. So let's try a slightly different one. What if they got not 8 times closer, but 8 times further apart? How would you handle that one? So what?
You just divide them.
Yep. So you would take the old force and divide by what number?
Take the old, divide by 64.
Yep. And that will be a new force that's much less than the original value, right? 64 times less, right?
Yeah.
Yep. So when they're close, again, moving closer, you take the old value and multiply it by some number to make it represent a stronger force. If they're getting further apart, you take the original force and you divide by some factor so that you're representing a force that's been weakened by some amount. Okay, good. Number 10. You want to give it a try? I think you actually... Yeah, I think you, again, I think you have the ability here without me doing too much. The one thing I'll save you the time of looking up. You might have remembered it, but is that the gravity constant G, capital G, is 6.67 times 10 to the minus 11, and the value for K, the electricity constant, is 9 times 10 to the 9th. Oh, the other thing that you have to find out, because see how they want you to compare how, so here, let me show you the picture. What they're doing is saying, hey, you've got a proton in the center of the nucleus, right, in the atom, and then you've got an electron that orbits around like this, right? And so the distance between them is now from here to here, right? And that's really the radius of the atom, because the nucleus is in the center, the proton is in the center, and the electrons are around the edge, and it goes in a circular orbit. And the other part that they didn't tell you was, since they want you to calculate the gravity force, what other thing would you need to look up? Which I'll just write it down for you, but I want you to identify it on your own. In order to calculate how much gravity exists between that electron and that proton that I just drew, what other thing would you need that they didn't give you? What's that? So, yeah, to calculate, because in this problem, they want you to calculate how much gravity force there is between this electron and this proton. And then they're going to want you to calculate how much electric force there is between this electron and proton, and then compare them. So my point is, what other thing would you need to look up in order to calculate the gravity force between an electron and a proton? Yeah, exactly. So I'm going to, I'll write them down for you. The mass of an electron is 9.11 times 10 to the minus 31 kilograms, while the mass of a proton, that one is only the electron I do. I don't remember the proton. That one I'm looking in my book. The electron, most electrical things when I was in college have to do with the electron because electricity is all about electrons. So there were so many problems that we used the value for the mass of the electron that eventually. Exactly, just like your phone number, you reference it only a handful of times and eventually you remember it.
Okay.
But the proton, I didn't use the proton's mass too often in college, so I'm looking that one up. It is definitely heavier. You should know the electron is significantly lighter than a proton. But that I should have in my book right here. There it is. 1.67 times 10 to the minus 27. So I'll write that down. 1.67 times 10 to the minus 27. So those you would have needed to look up, but I was getting to you. What's that?
So they want you to find both the electron force and the gravitational force.
You got it. They want you to evaluate those fundamental forces of nature, gravity and electricity, in terms of the forces involved at that distance, and then compare them so that you can conclude which force is so much stronger than the other.
Q1 would be the electron.
Yep, you got it. So you're recognizing that you need to reference the elementary charge, right? And that was
1.6.
Yep. Yes, sir. And do you have to even pay attention to the sign plus or minus?
No.
Not really. I mean, they're just looking for total quantity of force called the magnitude. So you could just drop the negatives out.
Okay.
Which force? Gravity force or electric force?
Electric force with the electric force, I got 8.2.
Okay.
and negative 8. And also the gravitational force.
So I got 8.2 times 10 to the minus 8
Yeah, that's what I got there.
for the electric force.
That's what I got from the other.
Okay, in magnitude.
I'm doing the gravitational force right now.
Okay.
Well, mass 1, gravitational force would be 9.11 times 10 to the negative 31st, 31.
Yep, exactly. Appreciate how small that number is.
Oh, wow, you're showing how.
I wanted you to see it because you have to see that at least once in your life to really come to appreciate that mankind has been able to measure something that's that small and that accurate, and be able to not only detect it but measure it and accurately measure it. I mean, that's quite an achievement of mankind.
Oh, wow.
It really is. To me, that's mind-boggling. Yeah. All right, working on the gravity force. Yeah, you already have the same distance to squared stored as x.
Yeah, so, I got a 1.01 and maybe still a negative 67.
Is it? Okay. I got.
Now I got 3.61 times 10 to the negative 47.
Yeah, that's what I got. So first, stronger force. You compare the two, which are on the board now.
The electron force.
Yeah, right. Way stronger. Is it because they were at different distances? You hold the proton and the electron at the exact same distance and calculate the gravity force and the electric force separately. But that difference now has nothing to do with them being different distances. They're held at the same distance. It's purely because electrical forces are so much stronger than gravity forces. So to actually finish this problem off, they ask you to do that. Notice they ask you to do a ratio. The last sentence says, what is the ratio of these two forces? So how can we do that? Which is the bigger one of those two numbers? Because ratio should always be, in my opinion at least, a bigger number divided by a smaller number. When they say do a ratio. So who's the bigger number out of those two? Yep. So you should put that in the numerator. And then divide by the smaller number, which is 3.6 times 10 to the minus 47 newtons.
And then use the map and divide it up.
Yep, divide it out, because that's what they wanted to do for that problem.
And then 2.9 times 6 and the negative 54.
I didn't get that, and I just erased what I had. What was in the denominator? 3.61 times 10 to the what?
That's a negative 47.
Okay, let me work 8.2 times 10 to the minus 8 divided by 3.61. I think you got to try that again. It should have. Yep, you want to divide. Yep. That's how many times stronger the electric force is than the gravity force. Because notice in the denominator was the electric force. I didn't mean that. Notice that in the denominator you had the gravity force, the small one. And in the numerator you had the much stronger force, the electric force. So we're finding that the gravity force divides into the numerator, divides into the electric force. How many times? 10 to the 39th times.
Yeah.
That means that the electric force is 10 to the 39th times bigger, stronger than the gravity force.
Gotcha.
That's crazy, right?
Yeah.
10 to the 12th. 10 to the 12th is what word?
10 to the 12th.
Trillion.
Trillion.
So what would 10 to the 12th times 10 to the 12th, which we would normally call 10 to the 24th, that would be called a trillion, right?
Mm-hmm.
A trillion times greater than a trillion is 10 to the 24th, right? What if we do 10 to the 12th times 10 to the 12th times 10 to the 12th? That's 10 to the 36th. We're getting close now to the 39. That would be a trillion times a trillion times a trillion, right?
Yeah.
So we're talking, that's how many times stronger electricity is than gravity. A trillion times. Times 1,000, actually, to add 3 more zeros to it. Be 1,000 times, 1,000,000,000 times, 1,000,000,000 times, 1,000,000,000,000 times stronger than gravity. I mean, it's mind-boggling. It's a significant, significant force. For that reason, when they design monitors and things like this, because the electrons are moving, and even like old projection screen TVs, they would literally fire electrons out of a little gun called a cathode ray gun in the back of the TV. And on the old projection screen TVs, that electron would then fire straight towards the screen and then hit the screen and generate some light when it hits the screen. And so the force that's propelling that electron from the back of the TV to the front of the TV is all electrical force. Based on our results, do you think they have to worry about gravity causing the electron to fall that significantly much as it moves towards the front of the screen?
Of course not.
Of course not, exactly. They don't even have to think about it. The force of the electrical force that electron feels as it flies toward the front of the screen is so many times stronger, as we just said, 1,000,000,000,000 times 1,000,000,000 times stronger than gravity, that they can actually pretty much ignore the effect of gravity, which is technically pulling it downwards.
You will not make a difference in calculation.
Correct. My point is, if you took a gun that could shoot electrons and just held it in your arm like people normally hold guns, and fired the electrons straight out horizontally, would it curve to the ground? Yes, it would. Yes, it would. So I want you to realize that. That electron still has gravity. It still has weight. And if there were no other really strong forces that it felt, it would curve in a trajectory just like a bullet would. My point is, inside the TV, does it feel any other really strong forces? Yeah, it's the electrical force that's spitting that electron out at huge speeds, and it's actually being attracted to a positively charged screen. The screen is positively charged because opposites attract, right? So they charge the screen up with a positive charge, and the electron gets fired and attracted to the positively charged screen by a force that's so much stronger than the weight of the electron pulling down, that because of that strong electric force that's present, they can just ignore it completely.
Gotcha.
Yep. Let me just, because we're almost out of time, I want to at least, I definitely won't have time to do this one with you, this next one, but I want to show you. Hopefully your teacher can help you with it. But I have 5 minutes, I have enough time to just show you the idea. So you get a square. This is the one that, this kind does turn up on the AP exam, the one we're doing right now. Okay? And they say that they're going to put, we're looking at number 14. They're going to place 6.15. What does that prefix say that you're looking at on number 14? What does the MC mean? Good. Good job. Yep. Milli Coulombs, which means when we put that into a calculator, what will we type in? 6.15 times 10 to the, what's milli? Good. Yep. And since they didn't tell us it was a negative, we would assume it's positively charged. And they're putting that amount of charge at all 3 points of a square. Here.
All 4.
Yep, at all 4 points. And lastly, at this point too, right? So all of them have equal charges, all equally distributed to each of the corners. And all of these distances are equal also. Okay? And it turns out that that distance is 10 centimeters, 0.1 meters. So what they're going to ask you to do now is evaluate. This is a significantly more challenging problem than what we've been doing, so you know. Now what you're doing is trying to find out what the magnitude and direction. It can take quite a while. I actually think that's crazy to ask someone to do all of them. I'm just going to show you one. How can we figure out the total force acting? We're going to evaluate all of the forces that this guy right here feels, okay? And we're going to do it conceptually first. I'm going to draw a free body diagram for that charge. So this guy is going to be in this free body diagram, okay? And I'm going to refer to the top left charge as charge 1. I'll refer to the bottom left charge as charge 2. The bottom right charge is charge 3. And the one that we're going to be evaluating for this 5-minute example is going to be charge 4, okay? Jeremiah, are you there?
Yeah, I got you, yeah.
Okay, so in which we're only focused on the top right. Which way will the top right charge move just due to charge 1? We're ignoring charge 2 and ignoring charge 3 right now. We're going to come back to them later. If only charge 1 and 4 existed, which way would charge 4 move if they're all positive charges?
Right.
Yep. So there'll be an electric force, and I'll label that Fe with a 1 to indicate that force is from charge 1. All right, are you with me?
Yeah.
Now we say, which way will charge 4? We're just focused on charge 4 the whole time. Which way will charge 4 move just due to the force felt from charge 2? Now we ignore 1 and 3 and just hone in on 2, 4. And say, which way will charge 2 apply a force to charge 4? Remember, they're all positively charged.
To play 1 to the diagonal.
Yep, up and to the right, right?
You're right, yeah.
Yep. So I'll put Fe2 to indicate that's the force from charge 2. The very last one that we have to look at is now charge 3. Which way would our charge that we're looking at move just due to charge 3's force?
Upwards.
Upwards. So to find out the overall net force, we're going to have to add all of these forces together using vector addition.
Yeah.
And that's challenging. That's not something I can do with you in 2 or 3 minutes. But I can still show you the idea.
Okay.
So will Fe3, this one here, be an equal force in length to Fe1? Would those be equal length forces, equal magnitude forces?
Yes.
Yes, because the force depends only on distance. And when you're looking at distance from charge 4 to charge 1 is 0.1 meters. Isn't it also 0.1 meters to charge 3? Yeah, so the distance between 4 and 1 and 4 and 3 is the same distance. Don't they all have the equal charges?
Yes.
Yes. So however hard, again, if we focused on charge 4, he's pushed up, let's just say, to illustrate an idea, he's being pushed up with 10 newtons of force from charge 3. How hard is he being pushed to the right from charge 1? If it were 10 newtons upward. 10 newtons to the right. Does that make sense? We don't know that it's 10 newtons. We're going to have to calculate it. But that's the idea. Those are equal forces, right?
Yep.
Just different in direction.
Yep, exactly.
So let's go like this and delete that because we don't know what that is. So how can we add these two together? It's called the head-to-tail method for vector addition.
Okay.
So you go like this, plus you put its head and tail of these two vectors together. So this is Fe3, and this one is Fe1. And the net force of just those two is this right here. It's called the resultant.
The resultant, yeah, I remember this.
Yep.
Okay.
So this right here is force for just 1 and 3, because we have ignored charge 2 for the time being, right?
Yep.
So let's stay with this. How would you figure out how long Fe3 is? Could you use Coulombs' law to figure out Fe3?
I believe so.
Right? Can you use K, Q1, Q2 over R squared and use it to figure out the force between charge 4 and charge 3? Yeah, because they gave you the charges in both cases, and they gave you the distance, right? So this problem is a whole bunch of tiny problems all built into one. So you'd have to work out what that amount of force is using Coulomb's law. Does that make sense?
Right.
Let's say, for example, that comes out as, again, 10 newtons. It won't, but let's just say it did. What will the vector to the right be? If it was 10 newtons to the upwards, then this would be 10 newtons to the right.
Right.
They were equal. We already rationalized that out, right?
Yeah.
What will this angle here be, do you think? If it's a square divided in half.
45.
Yep, 45 degrees. So we could now recognize that. Let me erase this a little bit to make more space. To find F net, you could use Pythagorean theorem, couldn't you?
Yep.
If it was 10 up and 10 to the right, then this would be equal to the square root of 10 squared plus, you know that? You'll have to work out what those values are. It's not 10. I'm just showing you that so you get the idea. So you'd use Coulomb's law to work out what that value is. Yeah? Make sense? Jeremiah?
I do see that, yeah.
Okay. Because after that, you now know what the sum of the force from charge 1 plus the force from charge 3 is. Which direction will it be?
Upward.
Up and to the right. Right? Which way is charge 2 pushing?
Charge 2 is pushing upwards and right.
And to the right. So, well, if you look at what I'm drawing, you'll have a force from this guy coming from him plus the other two that you've already added together.
Mm-hmm.
Does that make sense?
Yeah, I see.
How will we work out what this guy's force is right here? Do you know how much charge they both have? Because now you would have to focus on 4 too, the top right and the bottom left. Do you know how much charge they both have? 6.15 millicoulombs is the charge on all of them. Right?
Since you say like the force for 1 and 3 was 10. So.
I just made that up though, just to show you an idea. You'll have to use Coulomb's law to work out what that value is. So that'll be, you'll have to use Coulomb's law, which I'm circling here, and you would have to put in 6.15 times 10 to the minus 3 on both of those, right?
Yeah.
And then R would be the value 0.1. Mm-hmm. Remember to square it. When you get that, that takes the place of what I wrote as 10. I just wrote 10 to illustrate an idea to you, to show you that if it was 10 up, then it'll be 10 to the right. I don't know what the value is. You'll have to calculate it using Coulomb's law. So if you got the number 20 from what I just showed you, Coulomb's law, then it would be 20 up and 20 to the right. If you get 50 newtons out of Coulomb's law, it'll be 50 up and 50 to the right. I have no idea what you're going to get from Coulomb's law. Right?
Yeah, I'm just right.
And then lastly, because I have to get going, is that how can you work out the last part, which is charge 2 is sitting here and charge 4 is sitting here. If you look at the triangle I'm drawing, and if you know this is 0.1 meters from here to here, and also that you know it's 0.1 meters from here to here, how could you work out the distance along that diagonal? Yeah. Yep. Exactly. You'd have to use Pythagorean theorem to work out the distance between them. And again, you would have to use Coulomb's law to work out how hard charge 2 is pushing charge 4 up and to the right. And once you have that, that's what I'm starring right now. For the other one, because they're in the same direction. So if one of them came out as, I don't know, 8 newtons, and the other one previously came out as 15 newtons, then what would the net force be? 15 plus 8, it would be 23 newtons in which direction? Up and to the right, which is a direction of 45 degrees. So it's a lot of things, a lot of steps in there right now. But you can always watch this video again, right? You knew that, right?
Yeah.
So the only thing is that those numbers, I haven't done any calculations. I've just tried to describe the process to you.
Gotcha.
All the numbers I was using, 10, 8, 15, those are all made up numbers.
I actually did it by a very large number.
Yeah, I would expect that, because are they close together? 6 millicoulombs, a distance of only 0.1 meters, is only 10 centimeters. So I wouldn't be surprised. And also, 6 millicoulombs is a lot of charge. It's a lot. It's only in the thousandths of coulombs. The other problem you were doing was in the microcoulombs, which was millionths of a coulomb. These are only in the thousandths of a coulomb. So that's a lot of physical electric charge to have at only 10 centimeters apart. So if you're getting a large number, that wouldn't surprise me, actually.
Yeah, 34 million to be exact.
Yeah, I wouldn't be scared of that answer. But that's that. That's how you do that one. And number 16 is something I could help you with, but we're out of time. Hopefully your professor can maybe help you with number 16. That's the last one on your homework assignment. Yeah. All right, Jeremiah. I hope that helped you.
Thank you very much.
All right, you're welcome. And I'll catch up with you next week. All right.
Yeah.
All right. Talk to you later. Bye-bye. Okay, that concludes the lesson. Current time 9:08. Again, that was with Jeremiah from Boston Dream Academy. Date is March 9th. Lesson began at 7 p.m. and concluded at 9:08 p.m. What the heck?